So here we're taking a look at the graph of the polar equation r is equal to 1 minus 2 sine theta. And if we start here at theta is equal to 0, then here's what we will have. We will get this point on our polar curve when theta is equal to 0. Sine of 0 is 0. 2 times 0 is 0, and 1 minus 0 is 1. So we get this point with polar coordinates r theta, where r is 1 and theta is equal to 0. And then we go to theta is equal to pi over 6. What happens at pi over 6? We have sine of pi over 6, which is 1/2. 2 times 1/2 is 1, and 1 minus 1 is 0. So we get this point at the pole where we have polar coordinates r theta, where r is 0 and theta is pi over 6. In example 2, we want to find the area of the region that is between the inner and the outer loops of the Limacon. So now you start sketching the inner loop of the Limacon as theta goes from pi over 6. And when you get to theta is equal to pi over 2, you get this point on the polar curve. When theta is pi over 2, you have sine of pi over 2, which is 1. 2 times 1 is 2. 1 minus 2 is negative 1. So you have this point with polar coordinates r theta, where r is negative 1 and theta is pi. And of course, the radial line pi is over here. So you have a point on the opposite ray from the terminal side of our angle. And then as theta continues to go from pi over 2 to, this would now be 5 pi over 6. Sine of 5 pi over 6 is 1/2. 2 times 1/2 is 1. 1 minus 1 is 0. And as theta goes from 5 pi over 6 to pi, you have r values that are once again positive. And when theta is equal to pi, sine of pi is 0. 2 times 0 is 0. 1 minus 0 is 1. And you get this point with polar coordinates r theta, where r is 1 and theta is pi. And then you keep going. And here you get to theta is equal to 3 pi over 2. And you have this point on the polar curve. And the polar coordinates would be sine of 3 pi over 2 is negative 1. 2 times negative 1 is negative 2. 1 minus negative 2 is 3. So you have this point here with polar coordinates r theta, where r is 3 and theta is 3 pi over 2. And you keep going. And here you get to theta is equal to 2 pi. You complete the loop, but then you can keep going beyond that because you just keep going and with your angle of rotation. And if you keep going after one complete revolution counterclockwise, you will have angles such as, for example, 13 pi over 6. 13 pi over 6 is coterminal with pi over 6. Sine of 13 pi over 6 is 1/2. 2 times 1/2 is 1. 1 minus 1 is 0. So when you have 13 pi over 6, you're once again at the pole, once again at the beginning of the inner loop. Or you can think of it this way. What happens if you just look at theta going from 5 pi over 6 to 13 pi over 6? Let's look at that. 5 pi over 6, 13 pi over 6. You just get the outer loop. If you just go from 5 pi over 6 to 13 pi over 6, you're just going to get the outer loop. So if you have the limits of integration going from 5 pi over 6 to 13 pi over 6 in your integral, you're just going to get the area within the outer loop. And if you have the limits of integration going from pi over 6 to 5 pi over 6, you're just going to get the inner loop, pi over 6 to 5 pi over 6. That would just give you the inner loop. So, so the problem that we're dealing with requires us to have two integrals. One will give us the area of the inner loop, and the other will give us the area uh, contained by the outer loop. But in our problem, we want to find the area of the region that is between the two loops, so we have to subtract those two areas. And of course, if you want to see the whole thing once again, let me go from 0 to 2 pi would give you the whole thing, but we can go to 13 pi over 6. And there it is. So again, we want to find the area of the region between the two loops. So we have to find the area of the region inside the inner loop, the area of the region inside the outer loop, and subtract the area of the region for the inner loop from the area of the region inside the outer loop to get the area of the region between the two.